Hello and welcome to this Anritsu video podcast. My name is Enrico Brinciotti, a RF and microwave business development engineer at Anritsu. In this episode, I will introduce and discuss the real-time analysis capabilities of the Anritsu's new Fieldmaster Pro MS2090A Field Portable Spectrum Analyzer. The agenda for this session includes a description of what is an RTSA and how is it different from a conventional spectrum analyzer. In order to really understand the RTSA, we will also dive a little bit into the digital signal processing. We will then define what is the probability of intercept, POI, which is one of the key specifications of RTSA. Also, because RTSA calculates the FFT measurement results so quickly that the display cannot keep up, different types of display modes need to be used to show the results in a meaningful way. I will then conclude with some really nice captures from the field and an overview of the specs that make the MS2090A the world's highest performance handheld real-time spectrum analyzer. So let's see, what is an RTSA? Well, conventional swept spectrum analyzer and vector signal analyzers have blind times, and as such, they do not see every single event that happens. In particular, they struggle to capture elusive transient events. On the other hand, the RTSA allows for continuous gapless capture and analysis of the signal within a certain bandwidth. Let's look at the differences between RTSA and conventional spectrum analyzers. A swept-tune spectrum analyzer scans the input by sweeping its local oscillator, LO, to downconvert the input frequency range into a fixed intermediate frequency, IF, which is then filtered by the resolution bandwidth or RBW filter and detected. Now, what happens when we have a transient signal? Well, as the LO is swept, the input signal frequencies are effectively swept past the fixed frequency RBW filter. In effect, the spectrum analyzer can only see a small portion of the frequency span at any single moment. Therefore, the signal is visible only when it happens or it appears at the RBW filter at the right time and the right frequency. More modern spectrum analyzers are based on a fast Fourier transform. Here, the IF signal is digitized by an ADC, and they use the FFT to calculate what the frequency spectrum is. Instead of continuously tuning the LO, they use a step tune LO. So each FFT can process a certain amount of samples, and the LO just steps along in discrete steps. Also, this type of analyzer is blind to transient events, because to acquire enough samples to do the FFT, the local oscillator has to stay parked, acquire samples, and calculate the FFT. And while it's doing that, if there is any kind of signal that it's happening, it's not going to show up in the FFT and therefore not in the display. A vector signal analyzer downconverts the signal of interest within a certain bandwidth to a fixed frequency IF. The local oscillator is stationary and parked at a very specific frequency. The IF analog signal is sampled by an analog to digital converter, ADC, and a stream of time domain samples can be used for the modulation domain analysis. For spectrum analysis, the time domain samples are transformed into a frequency domain spectrum using FFT. The FFT processes a block of samples, also known as sample frame, and the number of samples in the sample frame is referred to as a sample frame size or FFT size. When the FFT calculation is finished and the results are transferred to the display, the next sample frame is acquired. So although the local oscillator is stationary, unlike the swept spectrum analyzer, the vector signal analyzer is still blind to signal events occurring in the time gap between sample frames. What sets an RTSA apart is its ability to continuously acquire samples of the signal and perform simultaneously the FFT analysis. And these slides illustrate the difference. The RTSA architecture is very similar to a VSA in that the LO is stationary. Because moving it implies allowing a certain time for the LOs and analog circuitry to settle, which means that the spectrum analyzer is blind during the settling time. So for RTSA, the LO is still part of the signal frequency of interest. The fundamental difference is that non-RTSA spectrum analyzers or vector signal analyzers using FFT analysis have a serial process flow to acquire the samples and calculate the FFT, whereas the RTSA has a process flow which is parallel, and it can acquire a new sample frame while simultaneously performing the FFT on the previous sample frame. So this parallel processing requires very fast digital hardware and a large memory buffer. RTSA spectrum analyzers like Anritsu's Fieldmaster Pro MS2090A are capable of performing 527,000 FFTs per second for a 512 points FFT. The number of points of an FFT is the number of frequency points that spans the FFT analysis bandwidth. It is also equal to the number of IQ samples collected in a sample frame. The more points, the finer the frequency resolution. However, the FFT computation time increases. There are certain digital signal processing concepts that are crucial for understanding the specs of an RTSA. A typical DSP flow is described here. The final IF is digitized by an ADC, and it goes into a digital down converter, which converts it into INQ at baseband. Then the FFT analysis is performed, and the VBW is a running average of the FFT samples on a frequency by frequency basis to smooth out the trace. Finally, the display detection section controls which amplitude value is displayed to the user. In a DSP signal flow, a common misconception is that the sample rate must be at twice the highest frequency, and that's really not true. In fact, the sample rate must be greater than twice the signal bandwidth. Two types of sampling exist: low-pass sampling, where the signal is between 0 and half the sampling rate, and bandpass sampling, where the signal is greater than half the sampling rate. Now, you might have heard that it's bad to sample signals if you're above half the sampling rate because of aliasing. But actually, if we choose the input signal carefully, we can avoid any aliasing problem while actually taking advantage of aliasing to do a down conversion. This down conversion can be performed to the first Nyquist zone as long as the sample rate and the final IF frequency are strategically chosen to actually take advantage of aliasing. As shown in the diagram here, a pass filter is needed to reject aliasing from unwanted Nyquist zone. In the MS2090A, the sample rate is 400 megasamples per second. Therefore, signals anywhere in these rectangles will convert to the same first Nyquist zone. And in the MS2090A, the final IF frequency is 300 megahertz, so there is a filter around this frequency, so that none of these other aliases can come into the first Nyquist zone. So why do we need windowing? Well, when a block of samples are acquired for FFT analysis, the mathematics of the FFT presumes that the time domain signal is periodic with a period equal to the sample frame duration. And here is a simple sine wave that is sampled over a time interval. When the sample frame is analyzed by the FFT, the samples at the start and at the end of the sample frame create an unwanted discontinuity. And this discontinuity in the time domain causes the frequency domain energy to be spread out instead of concentrated at the frequency of interest. So this is called spectral leakage, and is very undesirable in FFT spectrum analysis, since the ability to resolve closely spaced frequency components with different amplitude is lost. Furthermore, the amplitude of the signal is no longer an accurate representation of the true signal level because the spectrum energy has already spread out. And finally, another undesired effect of spectral leakage is the reduction in dynamic range. Well, we can trick the FFT by making a signal looking like a periodic, and we do that by using a windowing, whereby the samples in the sample frame are multiplied by a window function that smoothly tapers the samples near the start and the end of the frame to 0. Thus, when these modified samples are presented to the FFT analysis, the periodic extension of this sample frame does not have a sharp discontinuity, and the spectrum leakage is reduced. Notice that each window function has a different main lobe width, The RBW filter bandwidth is equal to the 3 dB bandwidth of the window's main lobe, and it is controlled by adjusting the window length and the FFT input sample rate. The window length can be equal to or less than the FFT size. The Fieldmaster Pro MS-2090A spectrum analyzers uses a Kaiser-Bessel function with the RBW set by this formula that you can see here, which gives a much lower Skurts response. Since the span of one FFT is also controlled by the sample rate and FFT size, the RBW and span are interdependent, and this interdependence is noticeable in RTSA spectrum analyzer since the measurement is restricted to the span of one FFT. In fact, this is how, by adjusting the size of this window, we can synthesize the RBW filter when doing the FFT. The RBW is set by how big this window is and also by the sample rate going into the FFT. And this is important to know because it will come into play when talking about the RTSA span and POI. For example, to set a narrow RBW, the window length can increase until it reaches the maximum FFT size limit, and then the sample rate must be reduced, which then forces the span to be reduced as well. Non-RTSA spectrum analyzers can stitch together multiple FFTs to cover a wider span, but that requires tuning the LO. So windowing also serves to implement the RBW filter in FFT spectrum analysis. When the FFT analysis is performed, with a window function applied to the input signal sample record, the effect is equivalent to a bank of parallel RBW filters. In this figure, I show you a simplified version of the RBW filter band frequency response, separated by their -3 dB bandwidth across the span of one FFT. And you can notice that the RBW filter response is incomplete at the start and stop frequency of the FFT span. So because of this, the usable bandwidth is only about 80% of the full analysis bandwidth of the FFT, which is set by the input sample rate times the number of points in the FFT. So what happens when we apply the window to the FFT? Well, in effect, the frequency response is convolved with whatever input signal is present. So to summarize, the anti-alias filter bandwidth has to be greater than the capture bandwidth, and the sample rate has to be greater than twice the signal bandwidth. Multiple parallel RBW are synthesized in one FFT capture. And also this one is important. Only 60 to 80% of the capture is usable. And why is that? So frequencies close to the edges cannot be used because they do not provide a full symmetrical filter response. Since windowing tapers the timed samples at the beginning at the end of the frame to 0, transient signal events at the edges are lost. So overlapping is used to ensure that capture of these signal events is correct. And each sample frame for the FFT is partially filled with samples that were captured in the previous sample frame. Now, the amount of overlap in RTSA is limited to the speed of the FFT calculation relative to the input sample rate to the FFT. The maximum allowable overlap percentage is dictated by the FFT clock and sample rate. The FFT clock rate is the rate at which the FFT can process one sample. In the Fieldmaster Pro MS-2090A spectrum analyzer, for example, the FFT clock is 270 MHz, so that it can complete 512 points FFT in 512 times 1 over 270 MHz, which gives 1.9 microseconds, or 527,000 FFTs per second. So the faster the FFT clock, the higher the allowable overlap. A higher overlap results in a shorter signal POI duration. Well, POI, as mentioned earlier, is the minimum signal duration of the signal that the analyzer can capture at full amplitude accuracy with 100% probability. Now, what happens if we have the input signal shorter than the POI specification? Well, the amplitude would be wrong, a lot lower, and a POI is not a single number. We will see that it depends on the FFT size, capture bandwidth, sample rate, window size, and overlap. In FFT analysis, The spectral magnitude of the signal is affected by its duration and the moment where the signal is present relative to the start of the sample frame and the window function. The amplitude is proportional to the area occupied under the window function. For the same signal duration, the amplitude can differ greatly depending on when the signal burst occurred. The theoretical minimum detectable signal is equal to 5 nanoseconds in the MS-2090A, which is set by the maximum sample rate into the FFT, which is 200 megasamples per second. For full amplitude accuracy, the signal has to occupy the entire area under the window function. To guarantee this condition, the signal must stay on for the duration of 2 consecutive sample frames in the simplest case where there is no overlapping and the window length is equal to the FFT size. So, if FFT analysis is performed using overlapping sample frames, the required signal duration for 100% POI is then shorter. And you can see an example here that overlap is actually good for the POI because it produces the required duration to get the full amplitude accuracy. Here I'm showing a 50% overlap, so if my FFT size is 512 points, the overlap is 256, and my minimum required duration is 767. If the window length is smaller than the FFT size, as shown here, the required signal duration will be then shorter, thereby improving the POI. Since the window length is adjusted to change the RBW also affects the POI, and a wider RBW corresponds to shorter window length and a shorter POI. So based on what we discussed so far, here is a calculation of the required minimum signal duration for 100% POI with full amplitude accuracy. So let's consider an FFT size of 512 points, a window length of 32, FFT clock speed of 270 MHz, and an IQ sample rate into the FFT of 200 megasamples per second. Once calculated that allowable overlap is that is 132, we can calculate that for our best setup, we get a 2.055 microseconds POI. So now let's look at display types. The Fieldmaster Pro MS-2090A spectrum analyzer is capable of completing a 512 points FFT 527,000 times per second. This is much greater than the LCD display update rate, and a density display is then used to show the measurement results in a meaningful way. The density display shows the color graded intensity of a signal event. The warmer the color, the more frequent is the signal event. During the acquisition time interval, a number of FFTs are calculated and their measurement results are mapped into a heat map frame. So it counts the occurrence of an FFT measurement result that falls into a particular frequency and amplitude bin. The display amplitude range is divided into 320 bins, and the number of frequency bins depends on the FFT size and the span settings. So in effect, the heat map is a two-dimensional histogram for frequency and amplitude. So the user can select between two different FFT sizes via the Density Display Resolution menu. The standard 512 points FFT size allows for the lowest POI, as we've also seen before. However, the FFT frequency bin resolution is coarser and can cause the display to appear more granular at low RBW settings. The 1024 points FFT size allows a smaller RBW setting for a given span with less display granularity at the cost, of course, of a higher POI. A spectrogram displays spectrum versus time. Each line of the spectrogram is created from a normal spectrum trace with its amplitude values mapped to a user-adjustable color scale. Each line represents the detected amplitude of many FFTs during the user's settable acquisition time, anywhere between 50 milliseconds and 5 seconds. The spectrogram differs from the density display in that it does not provide any indication on the number of occurrences of a signal event during the acquisition time. It simply shows the maximum, minimum, or a sample value of the amplitude detected during the acquisition time at a particular signal frequency. And this figure shows an example of both a spectrogram on the bottom and a density display on the top. So before showing you really nice examples of our RTSA, Let's look at some specs and an overview of the specs that make the MS-2090A the highest performance real-time spectrum analyzer in the market. We have a 110 MHz RTSA bandwidth over the whole frequency range of the instrument, from 9 kHz all the way up to 54 GHz. Our RPW can be selected with a 0.1 Hz resolution anywhere from 1 Hz to 40 MHz, and this gives us a POI of 2.05 microseconds and a minimal detectable signal of 5 nanoseconds. All this is equipped with a really high performance front end with more than 160 dB dynamic range and a minus 164 dBm displayed average noise level. Here you see an RTSA capture of a 110 MHz Wi-Fi signal in the 2.4 GHz band. Using the density display, we can notice immediately what's happening within this band over time. We see the advertising channels of the Bluetooth signals as well as the data from the other 37 channels bouncing up and down. You also see several Wi-Fi bands, Wi-Fi channels flowing through the back, and the data is clearly summarized in the display. So if I switch the spectrogram view, I can see even more of the information where each of the different Bluetooth carriers, as they move through the channels, are shown clearly bouncing in their 2 MHz channels. Also, we see the advertising channels and as they cycle through the process, and the fixed Wi-Fi channels and the variable Wi-Fi channels as well. Let's take a look at another examples of a possible interfering the wireless telecom signal in the LTE band. If I look over at my real-time spectrum analyzer, my display, my density display actually gives me a lot more information of what's happening underneath that signal. I can see that I have my LTE signal with lots of power, but there is something going on in the middle. I have a CW signal that's jamming part of the LTE signal and interfering with the data that's happening there. So if I'm a technician, I can identify clearly that there is a signal there, and I can use an interference hunting tool to go and find that signal, troubleshoot it, and hopefully solve the problem. Finally, here's another example where we are looking at a 2.5 GHz spectrum with different signals. And we enable the spectrogram view. We build up a history of what's happening over a period of time. And we can clearly see the activity in the wireless access points here and here. And we can also see the Bluetooth low energy packets. As soon as the Bluetooth features is then enabled, if I have a smartphone, this goes into Empire scan mode, and you can see it here where it looks for other Bluetooth devices. So in this case, it's hopping in a fixed pattern, and that fixed pattern is clearly visible in the spectrogram and trace. So now, following the Empire scan mode, the phone at some point will connect to the speaker again and will be able to stream the audio. And there you go. So once the connection is established, it's no longer in Empire scanning mode. And if I play music, you can see that the Bluetooth activity with the black marks here representing the individual hop frequencies in the Bluetooth signal. It's also interesting to note that over the period of time, Bluetooth will exclude channels where there is an active wireless LAN signal. And this is known as adaptive frequency hopping, and it's a way of ensuring that the signal gets through even if in the presence of other transmitters. So if we now start to stream music again over the Bluetooth from the smartphone to the audio speaker, and we can see that the Bluetooth signal here at the top of the display is avoiding the area where the wireless LAN is present due to adaptive frequency hopping. What I'm now going to do is, if I have a microwave oven, I switch it on, and that's what you see. We can see just how much power radiates from the microwave oven, making it very difficult for the other signal in the ISM band to maintain communication. Last but not least, the RTSA can also be very useful to spot and analyze signals occurring below the display noise floor of a conventional spectrum analyzer. And in this example, you're seeing a real field capture of a 5G new radio signal. And one of the most important parameters for field testing in 5G is the SSB, synchronization signal block, which is typically at very low level and stays on for much longer time than the TDD downlink signal. And in this example, you can clearly spot where the SSB signal is and notice that, for instance, it has an offset, frequency offset from the center frequency. We are now at the end of this presentation about real-time spectrum analysis. Thanks for your attention, and for more information, please visit Anritsu.com.